All right, so this is section 2.2 in Math 146. We are going to focus on function transformations. Basically, it's shifting and rotating and um, reflecting and all that kind of stuff. Again, this is all something you should have seen for the most part in a prior class, but we're going to do this with a multitude of different types of functions just to get you used to it. This will be pretty much done without the aid of a calculator, so it's going to be important that we review as we go through this some of the base functions that you're going to need to know, because if you don't know what the base looks like and the properties there, it's going to be hard to shift them appropriately. So let's run through the basic shifts that you can do. You can have a vertical shift, which really just means that you are going to take the entire function and it's going to go up or down however many units it is you are shifting it. So the ultimate, not ultimate, but the idea is that if I have y equals f of x as my base function, and I were to add some value, which we'll call k here, if I was to add some value to the f of x, remember that f of x represents y, so if I add a value to y, I am shifting the entire thing up k units. Likewise, if I were to have y equals f of x as my base function, and I were to subtract k, then I would be shifting it down k units. So basically the way to think of that is if you have a positive number being added to your function, you're going up. If it's a negative number, you're going down. That one tends to be relatively easy and tends to make sense to most people. Now you can also shift things horizontally. To shift things horizontally, you're affecting the x value, not the y value. So your function, your base function, would have to have something added to the x value. So if I take something and I add some kind of a value in the parentheses to that x value, I am now actually shifting this thing left or right. And it's a little counterintuitive. There's a reason that this works that way. When we get to a couple of examples, hopefully it'll make sense. But when you add an h value to your x on the inside, you're actually going to shift it left h units. Likewise, if you wanted to shift it right, you would actually subtract h. That would shift it right h units. And the general idea behind that, so let me respell units, is what value would you actually have to plug in for h, or excuse me, for basically what would you have to plug in for your x to make the inside of that 0? And again, when we do an actual example, you'll hopefully see it. All right, you can, those are probably the two most common, by the way. We can compress and we can stretch functions. Oops, that is supposed to be in a different color. It's not working. There we go. We can compress or stretch functions. And you can actually compress or stretch functions both vertically and horizontally. Once again, to affect a vertical, you're going to do something to the y value. So, for example, if I want to compress or stretch something vertically, I'm going to multiply my y value, f of x, by some number. And we'll put an a out front and say that that's the number. So, it would hopefully make sense that if I wanted to stretch something vertically, a would have to be positive. So if a is a positive value, it's actually going to stretch the whole thing. I'm sorry, that's incorrect. if A is positive, A has to be positive, otherwise we're going to do something else with it. A actually has to be bigger than 1 to stretch something vertically. So just think about if you had some kind of a function, and again, we'll write an actual example up later, that you have, and you multiply the entire function by 2, well, now you're making the y value bigger faster for whatever the same value of x would have been. If A is in between 0 and 1, this will be a compression. So now you're going to take your function and multiply it by some kind of a fraction in between 0 and 1, like half. You're basically making the y values smaller for the same x value. So once again, that would be a compression vertically. If we want to affect something horizontally, let's go with orange. This is probably the most difficult one for most people to understand. You should make sense that you're affecting the x. So instead of putting the a on the outside to multiply it, we're going to put the a on the inside. And once again, this is a little counterintuitive. And again, a has to be greater than 0, because the reason that a has to be greater than 0 in both of these, if a is less than 0, basically you have a negative. That's a completely different transformation, which we'll talk about in just a few seconds here. But in order for us to stretch or compress something horizontally, so think about almost like if you had, and this is really dating myself, if you had a slinky and you opened up a slinky one way, or you pushed it, if you had the slinky laying on the table, you stretched it or pushed it together, that would be a stretch or compression of something horizontally, or even just basically like a rubber band. If you pull the rubber band one way, or if you compress the rubber band the other way, something like that. Anyway, in order to stretch something horizontally, it's going to be a stretch if A is in between, that's horrible, is in between 0 and 1. That will indicate a stretch. So again, think about multiplying or putting an a in there, so you'd have f of 1/2 of x. That's actually going to stretch everything out. If a is greater than 1, that will then compress it. So again, that's a little counterintuitive. So usually the things that are affecting the x are slightly counterintuitive when it comes to stretching, shifting, compressing, all that kind of stuff. All right, and then there's a couple of other, let's go with a couple other transformations here that we're going to talk about, and these are reflections. And you can reflect things in two different manners. You can reflect things over the x-axis or over the y-axis. So a reflection over the x-axis would be something like y equals the negative of your original function. So that would actually reflect something over the x-axis. So this would be over the x-axis. So basically think about like if your base function was y equals x squared, and I make it y equals the negative of x squared. So instead of having everything above the x-axis, now it would fall below the x-axis. So you would have reflected the entire thing over the x-axis. And if you want to reflect something over the y-axis, you are now affecting the x value. So it would be f of negative x. And if you kind of think about it, this kind of goes with the whole idea of the even function, where something is symmetric to the y-axis. So if you normally had a positive x, but now you change it to a negative x and you get out the same y value, you've reflected something over the y-axis. All right, and those are your basic transformations. So now let's go ahead and look at what we would have to do in order to determine some of these transformations. We'll look at a few basic examples, and then we're going to look at some rational functions, some root functions, and see how all that stuff works too. So we'll start off with some polynomials, which should make things a little bit easier. And I'm going to start off with, again, very base functions. And as we go through these, hopefully you will recognize the base functions that we're doing. So let's start off with something like y equals x squared. That will be our base function. And that is your parabola, y equals x squared. So f of x in this case will be x squared. So what if we wanted to shift this thing vertically 2 units up? Well, the new function would be written as f of x equals x squared plus 2. Notice how that is not grouped with the x, it's after the x squared. So all that does is, and I'm going to dash this even though it's in red, it shifts the entire thing up 2 units. So if I know the vertex is at 0, 0, the new vertex is going to be at 0, 2, and it's the same shape, it just gets shifted up 2 units. Likewise, and I am not going to draw this one on this particular graph, if I wanted to shift it down 4 units, that would be x squared minus 4, and the entire green thing would have just been shifted down the y-axis 4 units. Let's say that instead we wanted to shift this to the right 3 units. I don't know, I'm just making stuff up. So we want f of x, but we want this to be shifted to the right 3 units. So now since it's affecting the x, I'm going to have to put something in there grouped with the x. And if I want to go to the right 3 units, it's going to be x minus 3. So again, here's the reason why that is the case. If I want to shift it to the right 3 units, that means that the vertex needs to lie on the x-axis at x equals 3. Well, in order for that to work, I would have to substitute a 3 in here to x to give me that point 3, 0. I am substituting a positive 3, which indicates that that is actually the direction that we are moving the shift. So that would end up looking something like this. Again, same shape. Only thing that we've done is shifted it to the right. Let's say that instead we wanted to, so reflecting this one, by the way, because it's already an even function over the y-axis, wouldn't change a single thing. So we can, however, reflect it over the x-axis, which means we would have to make every y value negative. So we would write this as the negative of x squared, not to be confused with this. That is different. In this case, you would do the x squared first, and then the negative would get multiplied afterwards. Order of operations, you would do the exponent and then the negative sign because it's a multiplication. If you did it the other way around, you'd actually be doing the multiplying by the -1 and then squaring it, which is why it would have to have been in parentheses. So negative x squared literally just reflects the entire green one over the x-axis, so it looks something like that. All right, hopefully all of that made sense. That is a basic polynomial. That's your y equals x squared. That's one that you should definitely know. Let's look at a second example. And we'll include some stretching and stuff when we do this. Example 2. Let's say that we have y equals, or f of x equals x cubed. Again, the base function for x cubed looks something like that. A little too steep over there, something like that. It goes on forever in either direction. And I hadn't been talking about the domain and range of these things, but hopefully that's something that you know. Let's go back up here real quick. The domain, of course, being all of the x values. The domain of all polynomials is always going to be all real numbers. So from -infinity to infinity. Just write that real quick over here. The domain is -infinity to infinity. But the range, in this case, if you're going with the green one, with the original, goes from 0, oops, and it does include the 0, so we would have to use a solid bracket, and then it goes up to infinity. Now, depending on which way this thing is shifted, that range is going to change. If you look at the one in red, the range had changed because we shifted the entire thing up 2. Well, now that means that the bottom or the lowest y value is 2, and it goes off to infinity. If you look at the blue one, the range didn't change anything from the original green one because all we did was slide it left or right. It still takes on every possible x value. So again, the domain didn't change, but the range in this case would once again go from 0 to infinity. And then if you look at the one that we did in purple, well, now the range is quite different because this one actually hits 0 as its maximum, as the highest possible value, and it goes off towards negative infinity. So it actually starts at negative infinity and finishes at 0 and does include the 0. All right, so that's kind of the domain and range for example 1. Example 2 will actually be just a little bit easier to deal with because of the shape of this graph. So let's say that we want to shift this thing. Let's do multiple shifts. Let's say we want to shift it 1 to the right. No, actually, let's go left since we went right the first time. Let's say we want to go 1 to the left and down 2. So we want to take every point on this thing going 1 to the left and down 2 units. 1 to the left and down 2 units, which would kind of put that center right there. So basically, again, every single point would have been shifted 1 to the left and down 2. It's going to look kind of something like this. That one should have been extended up just a little bit more, like that. That is not the best drawing I've ever done, that is for sure. But again, it shifted everything left 1 unit and down 2 units. So how would we actually write that? So f of x would be, let's see, we wanted to go left 1 unit. So that's going to be x plus 1 cubed, and then down 2 units is minus 2. Let's say instead we wanted to vertically stretch this one. If I want to vertically stretch it, that means that I have to multiply the y value by some kind of a number which is bigger than 1. So let's just say we want to vertically stretch it by 2. So then it would be 2x cubed. And why does this vertically stretch something? Well, again, so for the same x value that I would have, let's just say that we plugged in 1 for x. If we plug in 1 for x here, the point that we would get out would be 1, 1. If we plug in 1 for x here, you would still get the x value of 1, but now your y value would be 2. So we've just made the y value bigger, quicker. So basically, it would look the same exact way that the green one did, only it gets steeper much faster and in both directions. It'll look something like that. So that would be a vertical stretch. If I wanted to shrink it vertically, I would have to multiply the x cubed by something in between 0 and 1. So for example, like a 1/2 x cubed. So now, if I were to plug in 1, what I would get out is 1/2. So when I'm at 1, now it would be 1/2. So really, it's going to look something like this. Kind of makes it a little bit flatter. And again, it compresses it, pushes it more towards the x-axis, whereas the red one kind of pulls it away from the x-axis faster. So this one, I'm sorry, I should have written this, would be a vertical compression. The one in red would be a vertical stretch. All right. The nice thing about this one is if you look at it, the domain and range for all of these are all the same. Once again, it is a polynomial, so the domain is all real numbers, negative infinity to infinity. And it doesn't really make any difference what kind of transformations we did to this cubic. The range is also going to go from negative infinity to infinity since the arrows go up and down on both directions. The function keeps going in every direction. So your domain and range on this one are exactly the same. All right, let's try what is called the inverse function. Excuse me, not inverse function, reciprocal function. So this will be our next example. So we'll start off with f of x equals 1 over x. That's the reciprocal function. And this one is very, very important graph. So what you should know is that if you plug in x equals 1, you would get out 1. So it'd be something like right about there. As x gets bigger and bigger, the fraction is going to get smaller and smaller because you're going to get 1 over bigger and bigger numbers. However, it's never going to get to 0. So basically, as x gets bigger, this thing is going to start to do this and level itself off here. As x gets closer and closer to 0, so like a half, a fourth, a sixth, or whatever you want to call it, 1 divided by a half is 1. It's basically 2. Well, it's not basically 2, it is 2. 1 divided by a third is 3. 1 divided by a fourth is 4. So as we get closer and closer to the y-axis on this side, the numbers are going to get steeper. And again, it's going to approach, but it will never actually touch the y-axis because there's actually no way for me to get 0 for the y value out of this. And that's because in order for you to get 0 in a fraction, the numerator has to be 0. Well, the numerator is always 1. It will never be 0. And then on the other side, on the flip side of this, if you plug in the negative values, it's going to do exactly the same thing, except that they're going to produce negative y values. So negative x values are going to produce negative y values. And if you think about what I just said, that would make this an odd function. And it is. So that's 1 over x. That is the base of 1 over x. As a matter of fact, let me write that in green since I drew it in green. All right. And so what we can do is we can actually do a couple of different shifts. Let's do like 3 different shifts all at once and see if we can figure out how this works. So if we want to take f of x to now be, actually let's write it as g of x since we're changing the function. We're going to now make g of x 3 over x minus 2 plus 1. So we've done a whole bunch of shifting here. I've got that plus 1 on the outside, which means this whole thing's going to shift up 1 unit. I've got a minus 2 grouped in the denominator with x, which means that the whole thing is also going to shift to the right 2 units. And then the 3 on top is actually a multiplier, because this could really be written as 3 times 1 over x minus 2 and then plus 1. So really that means this whole thing is going to stretch 3 units vertically. So let's see if we can take care of what this would look like. We are going to shift it 1 unit up, 2 units to the right, and then whatever we get there, we're going to multiply the y value by 3. So let's see if we can figure out how that works. And I may have slightly misspoke. There is really an order that we should follow these things in. You should probably do your reflections first, if you have any, which we don't in this case. Then you should look at doing your compressions or stretches. So figure out what your multipliers are first. It's kind of like an order of operations thing. Do your multiplications either by your x or your y value first, and then do your stretches or then do your shifts, your adding and subtracting left and right, up and down. It's probably the best way to do it. So the first thing we really should consider is multiplying everything by 3. So if we were going to do that, we would multiply, and the two easiest values to do are going to be these two right here, because that's the point 1, 1 and the point -1, -1. So if we were to multiply the y value there by 3, the x value there wouldn't change, but we would shift everything up 3 units, because basically we're taking the point 1, 1 and we're multiplying the y value right here, multiplying the y value by 3. So that would give us the new point 1, 4. Now I would have a new point up here someplace right around 1, 4. And exactly the same thing for -1, -1. We would multiply the y value by, why did I say 4? That should be a 3. I apologize. Making all kinds of mistakes. I really do apologize. We're going to multiply the y value of the one on the bottom here by 3 as well, and we should get 1, -3, -1, -3. Wow. So that point will be here. So now we've gotten ahead and taken care of that. Now, the left and right, up and down, that doesn't make any difference. You can do that in either order. So now I'm going to take those two new points that I have, and I'm going to shift each one of them up 1 more point. So up 1, literally that is up 1. And then we are going to shift everything to the right 2. So right 2 units might put it there. Right 2 units over here would put it, let's see, that was at -1, so it would be putting it right about here. And now the general idea is that these things are going to look like this. So we shifted everything up, right, all that kind of good stuff. We actually have a new asymptote, which I guess we really technically haven't talked about yet, but the shifting would look something like this. And then this one would do something like this. And that's what it would look like when you shifted it. Right, not necessarily the easiest one to see there. All right, let's look at 2 more. And again, this is not covering every possible thing that we could do. Just trying to give you somewhat of an idea. Most of this you'll have to be able to figure out. And again, you should be able to do these without the aid of a calculator. Let's look at exponentials. So we'll say that f of x equals, and in this case, we're just going to do, let's just do e to the x. I guess that'll be a good one to start with. Okay, so all exponentials in their base form take on this property. They look like this. Okay, we did talk about that before when we talked about some of the exponential problems that we were dealing with. Some of the key things here is that when x is 0, well, that's e to the 0. Any number to the 0 is 1. That is the intercept right there. That is 0, 1. Because e, once again, is a positive number and you're raising it 2 powers, the value that you get out of this can never be 0. And what you should see is, as this function moves off further and further to the left, it starts to get close to the x-axis, but it actually never gets there. The bigger and bigger you make your x values, your exponent, it just gets really big really fast. So basically, this thing is going to approach the x-axis unless it's been shifted, and that will change things. So we could shift the entire function down 2 units. Well, that would be e to the x and then -2. That would shift the entire thing down 2 units. Okay, it doesn't change anything as far as the fact that it's going to cross the y-axis when x is 0. It just shifts it down 2 units. So this would be like at 0, -1, shifting that y-intercept down 2 units. The more interesting thing is if we reflect them somehow. So we could reflect this one over the y-axis. So let's say that we wanted to reflect it over the y-axis. If we want to reflect it over the y-axis, we're affecting the x value. So that would be e to the -x. So all that does is it takes the entire green one and reflects it over the y-axis. So now instead of getting steep on the right-hand side, it's going to get steep on the left-hand side. It's still going to go through 0, 1, but then it's going to start to approach the x-axis going the opposite direction. So that would be a reflection. This one here is a reflection over the y-axis. By changing the base of the function, that also makes a difference as to how the function looks. So in this case, if your base, which in this case was e, but if it's a base which is in between 0 and 1, so if your base is a number, 0 is less than a is less than 1, then what's going to happen is you're actually going to have a decreasing function. It's going to look more like the orange one did. So the function will decrease from left to right. If your base is greater, not greater than 0, greater than 1, then it's basically going to be just like it looks right now. So the function will increase. So either by changing the exponent to a negative or by changing the base into a value in between 0 and 1, you can actually make this whole thing decrease. And while I am not going to actually graph this one because the graph is already getting messy, let's say that we had f of x, and that is negative e to the x minus 3. What would the shifts be there? Well, I'm subtracting something from the x. I'm not multiplying something, but it is grouped with the x. I am subtracting something, so that would indicate that we have shifted the whole thing right 3 units. And the negative out in front of the e means that we're multiplying the entire function by a negative value, which means that we are reflecting it over the x-axis. We are taking all the y values that normally would be positive and making them negative, or vice versa. In this case, it really is true that all the values were positive and we are making them negative. So it is good that you can recognize that that's what you would have done. Again, you should probably do the reflection first when you are graphing it, and then do the shifting of horizontal and vertical, up and down, left and right. All right, we're going to look at one more example, and this is going to be a logarithmic function. All right, so logarithmic functions. Again, the shape of a logarithmic function, again, this one's really important to know, looks like this. And the important part about where this intercept is, your x-intercept is at the point 1, 0. And the log function will approach the y-axis, but it will never get to it. And then as it goes off towards the right, it's just going to keep getting bigger. It just gets bigger really slowly. So if you wanted to shift a log function, it's exactly the same general idea. let's say that we wanted to move the whole thing to the right. Three units. So then it would be x minus 3. So then the whole thing would shift to the right 3 units, meaning that the x-intercept would no longer be 1, 0. It would be at 4, 0, and the shape would then be the same. One of the differences is that you now have a different kind of an asymptote, a vertical asymptote, which again, we really haven't talked about, but the vertical asymptote would shift from being at 0 to being at 3. And the way you can think about that is this has to do with your domain. Again, you cannot take the log of a 0 or a negative number. So I cannot plug 3 in here because that would give me log of 0. But I can plug anything bigger than 3 in there because I can do that. So your domain here would change to be that x has to be bigger than 3, or in interval notation, it would be 3 to infinity. And notice that I did not include the 3. It's a parentheses, not a closed bracket, because 3 cannot be included. And the range, if you look at the graph, the range of all these log functions is always going to be all real numbers, negative infinity to infinity. And I suppose we should talk about the domain and range of the exponentials above. The domain of all of the exponentials is also all real numbers, because x can be anything, but the range is going to be dependent upon the shifts. So in a standard one, the one that was in green there, or even the one that was in orange, because all it was a reflection over the y-axis, goes from 0 to infinity. But what you can notice is like the one in the blue, it's going to go down. Since we shifted everything down 2 units, it actually is going to approach, let's put this in purple, it's actually going to approach -2. So the horizontal asymptote there also shifted down 2 units. So your range is going to go from 0 to infinity to -2 to infinity, or basically it's going to follow your vertical shift. So whatever your vertical shift is, it's going to go from k to infinity, or if it gets reflected, it would go from -infinity up to k, because that would be your vertical shift. So when we go back down to the log, in general, your domain, again, is going, sorry, your range is going to be all real numbers, but your domain is going to be based upon the h value, which is the thing which is grouped with the x. All right, I think that is plenty enough for this video. I did not actually intend it to be this long, but I think that that is pretty important for us to understand some of the properties of some of these base functions. We will deal with more base functions as we go, but I think that's pretty good, and hopefully you'll be able to get the homework done for this section.